Hi everybody, so this is going to be a video for determining voltage drops using Kirchhoff's voltage law. And we're just going to go through and see if we can come up with a method that will allow us to calculate the voltages at each individual point. So what I can do is I can remember the principle that my voltage is going to be dependent on the current and the opposition. So I just want to use voltages. We've calculated everything. We have a source voltage of 120 volts, a resistance of 240 ohms, and a current of half an amp. So you could go and you could use the current that we calculated at each individual point to come up with the voltage drops. Absolutely. Okay, but what if you just were given this scenario and you were asked for voltages? You don't want to have to go through and calculate current. Okay, so we can use Kirchhoff's voltage law. So I'm going to start right here, because this one's kind of wide open all by its lonesome here. So what I can do is I can understand the principle that the percentage of the opposition is going to directly relate to the percentage of the voltage drop that it gets. So I'm going to take my 200 ohms and I'm going to divide it by my RT. Okay, so what that is R5 divided by RT. And I'll end up with 0.866 or 86.66%. It's 86% of the total opposition. That means it has to take 86% of the voltage. So then I just take my source voltage, multiply it by my percentage, which is 0.866, and that equals 100 volts. So I know the voltage across R5 is 100 volts. That means the remaining voltage of 20 volts is shared on the remainder of that circuit, which is nice because that is essentially from this node to this node. So already I can see that the voltage here has to be 20 volts. So when we went and looked at my equivalent circuit, I came up with an R equivalent. We'll call that R equivalent. When I did for R1, 2, and 4, when I added 22 inversely with 180 and then added that directly with 18, I got that as 90 volts. So when we did R1 and 2 inversely, these two were 72 ohms, and then we added that directly with R4. Okay, so R1, 2, and 4, that equaled 90 ohms. So I can kind of treat that as its own little equivalent circuit right now. And when I look at this, I can say, all right, so if 18 ohms divided by 90 ohms is going to give me the percentage of voltage of that of the 20 volts that I have remaining. So 18 divided by 90 gives me 20%, 0.2 or 20%. Now I can take my V and multiply it by that 0.2, and I get 20 volts times 20% or 0.2, and I get 4 volts. So I know now that there is 4 volts across that component. That means Kirchhoff's voltage law, there has to be 16 volts across R1, and because it's directly in parallel with R2, there has to be 16 volts across R2. If you want to verify that, which is always a good thing to do, when I set an R equivalent, I can do this in red, R equivalent for 1 and 2, we said that was 72 ohms. So I can say 72 ohms divided by 90 is going to give me the percentage of that 20 volts that those two components take, which is 80%, which is the remainder from that 0.2. We said this was 0.2, so the remainder has to be 80% or 0.8. So I take my voltage, multiply it by that 80%, which is 20 volts multiplied by 0.8, and I get 16 volts. What I love about this method is you can see how much quicker it is than Kirchhoff's current law. I love Kirchhoff's current law because it reinforces a ton of good information. But understanding the voltage divider principle and how that voltage is shared depending upon its equivalent opposition at those points is a very, very... Because now that I have the voltage across every single one and its opposition, I can quickly calculate current. So I hope this has helped. Those are our two methods. We can use Kirchhoff's voltage law or Kirchhoff's current law, or a combination of both, right? Like if I was asked for what is the current through R4, I don't have to go back and use Kirchhoff's current law. I have voltage and opposition. I can quickly calculate current. So it's good to be able to know both. I often get asked, Jason, which one should I know? Both. That's the answer. Both. You need to be confident and comfortable with both, because confident and comfortable with both will allow you to move back and forth and quickly and efficiently analyze circuits. So I hope this has helped, and I look forward to seeing you in the next one.